Okay, today is the 6th. And what we're looking at is given one vector and another vector. And we're going to project U on V. This is the projection of U on V. And we know how to find that projection. Okay? Take the dot product over the magnitude of V times V over the magnitude.
Is the magnitude supposed to be squared?
Yeah, well, you can do it that way too. You can square this times V or do this times the unit vector in the direction. Either way, they're the same. It could be.
The definition of the projection is always form the right triangle, right? Is that
Yes, always. Always. You could do it this way, but I think it's more useful in this problem to put it in this form. But this way is the same. This is taking the unit vector in the direction of V and multiplying by the magnitude. Now this would be the magnitude of the projection here. When you take the magnitude of the projection, that's what we have here. And that's how we derived the results. We found the magnitude of this, and we multiplied that magnitude of the projection by the unit vector in the direction of V. That's what this part is right here. Okay, that's the unit vector. Okay, so we have this. If you want this, it's the difference between U, this is the orthogonal projection here, call this W, where W would equal U minus the projection. Okay, it's the difference of those two. After all, if you complete this parallelogram here, the main diagonal of this parallelogram is the sum of those two vectors. The minor diagonal is the difference of those two vectors. So this is the difference of those two vectors. It's U minus the projection of U on V. So you could do a problem. Did you have a problem there to do? Did you know what the vectors were?
I don't remember what the components of the vectors were. I just remember this specific topic.
Yeah. Well, that will give you the orthogonal, this part right here, the other one. And if you need its magnitude, you just take the magnitude of that vector. That would work. Well, we could do one. You want to do one?
Yeah.
Let's do one.
I got one.
You got one?
Yeah.
Go ahead.
58 over 13 and 87 over 13. That's the projection.
So the projection of U on V is what?
58 over 13
Great.
and 87 over 13.
Oh, good. Good problem.
That's almost the Web assignment.
Yeah, I'm not surprised. All right. So that would give us this. All right. We need U as well, though. We need something else.
I didn't write you.
What's that?
I didn't write you.
Well, by itself, it's not helping. All right. We know the projection, but that's an infinite number of possibilities for that to occur. I'll tell you what. Let's start.
I'm sorry.
No, you're all right. That's fine. Yeah, tried to help out. That's fine. All right. Let's take U and is 1, 3. Let's take V is I don't know 6, 2, and let's do them both. Let's find the projection of U on V, and then we'll find the orthogonal, okay, projection. So, all right, everybody have this stuff? I'll do a new diagram. This is not anything we're going to need that often. I don't know if we actually need it again. The projection we need a few times, but this part of the projection, the orthogonal part, is not really needed. Well, we should do it. Okay, you guys ready? Okay, so here's what we have. You've got U is 1, 3. We've got V is 6.2. What we're going to do is drop that perpendicular. This is going to be the projection of U on V. Okay. So we want to find that. Let's do that first. That's the dot product over the magnitude of V times the unit vector in the direction of V. So, dot product, 6 plus 6 is 12. The magnitude of V is the square root of 40 times another square root of 40. So it's a square root of 40 squared is 40 times V. Let's see, we can simplify a bit here. Divide by 4 and divide by 4. So we get 3/10 that vector. That's the projection. To find this part of that, okay, what we're going to do, that's the orthogonal part, this other side of that right triangle. That's equal to U minus V, U minus the projection of U on V. And that's equal to 1/3 minus, well, let's take the 3/10. That would be 18/10. That's 9/5. Oh boy, these always come out messy, it seems like. And that would be 3/5. So we end up with this part right here. Negative 4/5 and 12/5, I think. Is that about right? Negative 4/5 and 12/5, okay. And what do we want? The magnitude, what did they ask for? The magnitude of that orthogonal projection?
Just the component.
Just the components, okay. Let's make sure I'm going in the right direction here, though. Okay. If we want this vector pointing downward like this, from there, I want this to be just the opposite. Negative 4/5 and positive will bring it up this way. I want it to come down. I'm going to have to take the opposite of this here. Okay? So it's the opposite of that I need for that from here down to here. So the actual answer would be 4/5, negative 12/5. Okay. You see what I mean? I had it going back up this way. We want it to come down that way. So that's what you got to do. Okay. All right. Anything else? Yeah, Dave.
So to find where either lines or planes intersect, you just set them equal to each other and find the common point.
Yeah, but it's not it's not that quite that simple. If you've got two lines to intersect, you set them equal, but you got two different parameters there to deal with. So you have an example of one? Yeah, no.
Can we do one?
Yeah, sure. Let's do one. Let's take two lines and find out where they intersect. So I have to come up with two intersecting lines, right? So I can do this. Come up with two intersecting lines here. Here we go. Here's two intersecting lines. You ready for this? X equals 3 plus t. Y equals 2. Yes.
I don't mean to interrupt, but on the test, is it going to be in parametric form like this?
Yes.
Okay.
Yeah, there's only two ways to get that equation of a line, parametric form or the symmetric form. The symmetric form is just hardly ever used.
Okay.
So this will be it. And z is equal to, I don't know, let's say something here. 1 plus 3t. Okay. There's one line. Here's another line. 4 plus 2s.
Would this be similar to an exam problem?
When I went through the list of topics. What did I say? Did I say specifically? If it's on there, then yes. I'm not, my question is, I'm not sure. I know what I give you a problem that given 2 points, find the equation of the line.
Yeah.
Parallel intersection skew, final.
Intersecting? Okay.
Not specifically, that's just like if it.
Yeah,
if they are
intersecting.
All right, okay. Then maybe it is.
Are you finding the point right now?
Yeah, I'm gonna find the point of intersection. Okay. That's what I'm gonna do. Now, that doesn't guarantee, because I always give a few extra topics that I want you to know that may or may not be on the test. I don't want you to just confine yourself to this set when it's probably this set that you probably should know, but I can't put all of those on the test. You know what I mean? Dylan? Oh, good. All right, that's all right. All right, that's okay. That's all right. All right, 4 plus 2s. This is something you should know how to do. Is it on the test necessarily? Not necessarily, but I mentioned it. It's something you should know. So let's do it. So 4 plus 2s. How about 3 minus s? How's that? Does that look good? Okay, hold on a second. T is 1, I get 4. S is 0. S is 0. No, I can't. It's got to be 2 minus s. I'm sorry. I'm sorry. I got to make these intersect. All right. Let's see. I got 4. Okay. Okay. So I'm forced. Okay, I'm forced to do this. Okay. So. I got it. I got it. 1. Okay. I got it. 1. Yeah. Got it. Okay. Here we go. Jeez, there must be a better way than what I just did. All right. Wow. I just took these 2 lines and I tested every single point on the 2 lines. So, you know what I mean? That's a little difficult. All right. So let's do this. What we're going to do is determine whether lines are the same, whether they're parallel, intersecting, or skew. We're going to find the intersection. We're going to find the point of intersection. Okay? Because that was the question. Okay. What do you do first? First, you find the direction vector for this line. 1, 2, 3. And you find the direction vector for this line. These are the coefficients. Okay, these components come from the coefficients of the parameter. 2, -1, 5. They're not constant multiples of each other. They are not parallel. They are not the same. That's done. Okay? Now, the question is, are they intersecting or skew? And this is what you do. You find out for what values of t and s, x and y are the same. So you set the x is equal, and you set the y is equal. You find the t and s that cause the x's and y's to be the same. And then you see at that t and for that s, are the z's the same as well? If they are, the lines intersect at that point. If they're not, they're skew lines. Okay? So that's what you got to do. At this point, I don't know, you solve for t here. This tells you that t is equal to 1 plus 2s. Okay. Substitute that t in for this t. 2 times 1 plus 2s is equal to 2 minus s. 2 plus 4s equals 2 minus s. Add the s to both sides to get 5s. Subtract the 2 equals 0. S is 0. If s is 0, put it in here. T is 1. At that point, for those values of the parameter, x's and y's are the same. You can check it out. T is 1, x is 4, y is 2. At s equals 0, x is 4, y is 2. So the x's and y's are the same for those values of the parameter. Now, take those values of the parameter, substitute them in, and find the z values. When t is 1, z is 4. When s is 0, z is 4. Yes, they intersect at that point. 4, 2, 4. Then,
And so what you're saying at the beginning of that problem is if they were the same line, those unit vectors would be the same numbers.
Not necessarily. These direction vectors would be a constant multiple of each other. Not necessarily exactly the same, but a constant multiple. That's all you need. Okay? Because you can get the same line with different coefficients as long as they're multiples of each other. As long as they're multiples, it would be either the same or parallel lines. And all you would do there is test one point in one and see if it's on the other. We should probably do one of those too.
Yeah.
Okay, we will do one of those. Dylan.
So 2 out of 3 of the coordinates are the same, that means they're parallel?
No, it does not mean that. What happened here was not only were these two the same, but the thirds were as well, so they intersect.
Well, what if like the third was?
Skew.
Skewed, okay.
Skew would be the thing, the alternative. At that point, there'd be skew lines. But we should do one like this where they're, say, parallel or the same. We will do it. Go ahead,
I
David.
think you kind of answered my question.
Oh, good.
Or he sort of asked it, but I was wondering, if you go through this first or this second step and get the T and the S, and you plug it into the first Z equation and you get one number, but you plug it into the second Z equation, you get a second number.
Mm-hmm.
If you get different numbers, does that mean that they're skewed?
Yes,
Okay.
definitely does. If the X's and Y's are the same and the Z's are different, skew lines. Okay? Absolutely.
In the events of like any other of the 3 were not the same, would it be the same deal?
Okay.
Y and Z are the same, but X's and...
Yeah, you could do that too.
Okay.
You could take any two. Yes,
And
that's
if,
true.
Like only 1 out of 3 were the same, does that just mean anything?
That would mean not a heck of a lot, because that wouldn't tell you very much. Because if exactly one were the same, I don't think you can get exactly one the same.
It's a little weird.
I think you I don't think you can get exactly one the same and the other two different, can you? Wait, if you had parallel lines, you could have the X's would be the X's would be the same. Y's would be different, and Z's two of them are the same. Even in that case, if they're the same line, then they're all 3 are the same. I don't think we can do it. What do you think, Teddy?
I don't think it's possible.
Well, then there it is, right there. All right, then it's not possible. All right, let's do one where we get either parallel or same, and I'll tell you what, I'm going to give you one. Yes.
No, you just pointed your pen like that, so I was right back at you.
Oh, okay, wow, all right. I
That's why
feel
I did a
something.
staring game with you. You stare at me, I'm just going to stare back. It's an enjoyable game.
Okay. All right, that's fair enough. Let's do this. Let's do this line. This time Z, I can just make up anything, right? Okay, let's say 2t, 1 plus t, and Z equals 3 minus t. There's one line. And here's another line. X is equal to, now what do we want to make it, parallel or the same? What should I do? Make it parallel or the same?
Tell us, parallel.
What's that?
Don't tell us.
All right, don't tell. Okay, you guys figure it out. Okay, got it. Plus 4t. Oh, S. It's got to be S. Got to be a different parameter. 1 plus 4s. 2 plus 2s. And I don't know if this will work. I don't think this works anyways. But anyhow, 4 minus 2s. All right. You tell me, what do we have of the 4 conditions? We've got 4 possibilities. Parallel, same, skew, intersecting. Those are always the 4 possibilities for 2 lines in
Wait, what was the
space.
second one? Parallel what?
Same.
Same, okay.
Parallel, same, skew, intersecting.
Come on.
What happened? What happened? Oh, you already gave the answer?
It spoils everything.
Oh, man. All right, take it easy. Hold on.
Chill, dude.
Just,
So you can just test any point.
yes.
and see if
Yes.
all three are the same for that point?
If you know that they're parallel or the same, all you have to do is test one point.
Any random number?
Random number. You take any,
All three have to be the same for them to be the same line?
correct. They'd have to intersect. The three coordinates of that point would have to be the same, yes. Yes.
Parallel.
You say parallel. Okay, he says parallel. Okay. All right, what does somebody else say? We got some other possibilities here? He says parallel.
I think parallel.
He says parallel. All right, anybody else?
I'm gonna say parallel.
Oh, wow.
Seal deal.
Well, that's it, man. Those three. Anybody would dare disagree with those three? That's, wait. What? Do you dare disagree with them?
Oh, no.
Oh, you don't? Oh, you don't dare. Okay. All right. All right.
I don't. Yeah.
Adrian disagrees with you guys. Do you disagree with those guys?
So if they're parallel, you can just plug any number in.
Yeah, but you got to be careful when you guys are saying that. I'm not sure if you mean, you got to find a point. If they have one point in common, all the points are in common. That's all you have to do. I'm going to show you what I mean, just to make sure we're okay. All right, here's what we're going to do. Direction vector, 2, 1, negative 1. Direction vector, 4, 2, negative 2. This is negative 2. This is 2 times this. Therefore, they are either parallel or the same. Okay? Now, to determine that, what we have to do is take one point on one and see if it's on the other. If it is, we're done, and they're the same. Okay? Because if they share one point, they share all their points, being parallel or the same. Okay?
So if we get to this point and we see they're a multiple of each other, this should be the first thing we check.
Yes, that's the first thing to check. That tells you parallel or the same. And if this is not a constant multiple of that, then they're either skew or intersecting. So, okay, so we know they're parallel or the same. There's various ways to do this. If I let t equal 0, for example, here, I've got the point 0, 1, 3 on this line. What value, that was not a good choice, was it? What value of s would cause x to be 0? Negative 1/4. When s is negative 1/4, I have my x to be 0. Okay? Now, what's y at that point? Y at that point is going to be 2 minus a half, 1 and a half, not equal to 1, done. Okay? They are parallel lines. Okay? Because if they were the same line, this point at 0 would also be the 1, 3. They would have those in common. Okay? So we know automatically they're parallel and not the same. Okay? You with me on that? I'm going to give you one more. I can give you one more. Let's just settle this issue. I'm going to give you one more.
Wow.
I know it. How about this? 1 plus t, 2 plus 3t, and z is equal to 2t. And let's have x equal, okay, so, oh boy, okay, so I want this. Okay, I got to figure this out here. 0, I want that point. Okay, so I want a 2s here. Okay, I want 2s, just 2s. And then y I want is, so, s minus 1. And z I want, boy, will this come out? I don't know. 0. Oh, I can't do that. It's got to be, oh, for Pete's sake, I'm sorry. It's got to be 6s, because I want it to be that. Boy, if this works, I'd be astounded. Okay? And the other one has to be 4s minus 2. All right, try that. See what you get. think I did it. I think it works. You got it? That's tricky, though. Try and come up with, that's not easy to do. Is to come up with these two lines with different coefficients here, but multiples of each other, that for different values of each, they come up with the same point. You know what I mean? Thanks for that. You're probably thinking to yourself, Burns, that was so simple, I can't believe it. That's okay. You got it, Dan? Yeah. Good. What's that? You got it? Yes. I got it. You got it. Oh, gosh.
I'm going to listen to these recordings for entertainment. I like so much method
Yeah,
and laughter.
it's true. We have a good time. Well, I don't see anything wrong with that. Omar.
I got different values for x. I think it's 10 points.
No, I'm going to put it on.
So wait, what are you saying, Omar?
I think I picked 10 points. I don't know.
Well, let's see. Anybody want more time? Wait, does that mean? What does that mean? Oh. All right. Adrian, you want more time?
No, I'm good for time.
We all set? All right, let's take a look. First thing you do is, like we said, take a look at those direction vectors. 1, 3, 2, 2, 6, 4. This is twice that. Either the lines are parallel or the same. Parallel or the same. And what you've got to do is just test 1 point. That's all you need. If you let t equal 0 here, you get the point 1, 2, 0. Now, what value of s would cause that to be 1? So the x's agree. Let s be 1/2. At 1/2, do we get the other two coordinates? 1/2 we get a 1. At 1/2 we get 3 minus 1, which is 2. At 1/2 we get 2 minus 2, which is 0. Yes, we get the three coordinates to be the same. They are the same line. All right, so Omar, what'd you do?
I'm not sure.
Oh, okay. All right. There are other ways to do that. The bottom line is, if they're the same, then all the points are the same. And if you get their x's agreed, then the y's and z's must agree too, if they're the same line.
Is there any particular way to make the point?
I think letting t equal 0 is a way to go. Sometimes it causes a fraction here. You can let s be 0. Maybe that would be... Actually, s equals 0 is probably an easier way to go, because then you get a 0 and t is -1. At 0, you get -1. When this is -1, you get the -1. At 0, you get -2. At -1, you get -2. That avoids the fractions. You could do what we did before. I don't think it's necessary, though. Set the x's equal, the y's equal, and then check for those values that z's would be equal.
Just gives you -1, -1, that.
Say that again now?
If you set them equal to each other, you can solve for like t, but then if you go to plug in the solve.
Oh, it turns out to be an identity.
Yeah.
Yeah, I see that. Yeah, I can see that now. So the way to go is this. Take a value for the parameter, see what the x, y, and z is for one line, and verify that that point's on the other line.
So in this case, these are the same lines?
These are the same line, yes. Yep.
So is this process the same for working with planes?
No, it's not. For planes, you've got a different situation. They're not given parametrically. They're given in terms of ax plus by plus cz plus d equals 0.
So you'd have to convert that to parametric?
No, you don't. what you do is, let's say you have planes that do intersect in a line. What you have to do is something a little bit different. That's when we had to use that.
The normals and the angles.
Geez, you could use the normals, but if you have two planes, let's do two planes. Let's take a look at two planes. Let's suppose we have one plane. I think we did one. I think we did one like this. Let's take one plane. So we have, let's say, that. Okay, so that's one plane. And let's take another plane. So we've got, let's say, 2x plus y minus z. Okay, hold on. I'm just going to make sure it comes out okay. So we can... okay, so we have two planes here. And what we did last time, we eliminated one of the variables in the two planes. We set the two equal, eliminated one variable. So we had x's in terms of y's. And what we ended up with is having the equation of a line if they intersect. So watch this. So if you add up these two equations, we'll get 3x plus 2y, z's will cancel, plus 34 equals 0. Okay. That tells us we have a line here that's the intersection of these two. We've got a line. So if you solve for y, oh shoot, all right, that's the way it goes. Okay. That line is common to both. So let's verify that. Let's take x equals 0. That's a point on this line. The y would be negative 17. If x is 0 and y is negative 17, we get negative 17 plus the 10 is negative 7, and z is 7, would be a point on this line, on this plane. Okay? You with me on that?
Where did the 7 come from?
The 7 came from substituting in 0 and negative 17 for x and y and solving for z in the first. In the second, when x is 0 and y is negative 17, we get 0 and negative 17 plus 24 is 7, and z also is 7 to make it equal to 0. Okay. That line is the line of intersection between the two planes. Any point that you take on this line will be on both planes. Take any point you want. Let x equal 0 and solve for y. Let x equal negative 2 and solve for y. That's the line, that's the equation of their intersection.
That seems pretty easy.
That seems real easy.
Now what if it's not that easy?
Yeah, right.
Like your Z's buttoned up nicely there.
Oh yeah, I know, and I designed it that way. Well, let's suppose the two planes. Now, how can two planes be related? Let's figure this out. Two planes can be related by being parallel. Okay, you got two parallel planes. They intersect in a line, or they are the same plane. That's it. There's no other way for two planes to interact. They can't intersect at a single point. They have to intersect in a line. Okay, so these worked out really nice. The z's just canceled out. You got two other situations: parallel or the same. What happens there? Let's suppose we have this. Now, how can it be parallel? It can be parallel if it has the same normal, or the normal is a constant multiple of the other. In other words, the normals are parallel to each other. Okay? So what would be the equation of another plane parallel to this plane?
2x plus 2y plus 3.
Perfect. I don't care what you use for a constant here. Now, it does matter for a constant. If I use a 20 here equals 0, what's the relationship of those two planes? They are the same. This is 2 times that. They're the same equation. Just divide this by 2. They're the same plane. okay? That must be the case if they're the same plane. It must be the same equation. What happens if we have this? What do we have here? Parallel planes, because they have the normals are constant multiples of the other. These are parallel planes. They're not the same. They're parallel planes. So what do you have? If the normal vectors are constant multiples, either they're parallel or the same, just like the lines, really. Okay, parallel or the same.
So the constant will decide whether it's
Yeah,
parallel or if they're the same plane?
exactly right. Exactly right.
What does the constant actually affect?
It moves it up or down. The constant will move the plane up or down. So you got two planes that are parallel, the constant will either move it up or down. If it moves it just right, they're the same plane. Okay? Now, how else can two planes interact? Intersecting. In which case you get this situation over here. Where when you do this and eliminate one of the variables, and you'll always be able to eliminate one of the variables. Now that was nice, but even if you didn't have that, you could multiply by something, so one variable is eliminated. Now, it's possible that you end up, no, that's it. I mean, you can always eliminate one
We
variable.
have different coefficients for like disease.
Yeah.
You just find a common multiple for the other one.
Absolutely.
Making the same.
It doesn't, yes, yeah. Make them opposite and
That makes it
add.
the same plane anyway.
Yes, yes. So there you go. Go ahead.
So do you always want to put the equations in the equals 0 form?
Find the equation of plane. I don't know if I do it this way or equals the constant. It doesn't matter. It's multiple
You always
choice.
wanna- Before you start manipulating them algebraically, do you want them to be in that form so they both equal 0?
You want them to have the x's, y's, and z's lined up. Where you put the constant doesn't matter. Either this side or this side. Doesn't matter. All right, what else you guys got?
To go home.
It's up to you. Hey, listen, this is for any questions you have on anything in the chapter. You ask. Dan.
I'm actually curious on something in the lab.
Okay, Dan, go ahead.
The first one here says plot y equals sine of x and x equals sine of y.
Yes, yes.
Is that are we supposed to do, plot the arc sine of y?
No. No, you ready for this? What's the first one I ask you?
Y equals sine of x.
Okay, let's do this. How would you do this? Y equals the sine of x. This is a parametric plot 3D.
They don't have a parameter.
You're going to make a parameter. That's what you're going to have to do. So y equals sine x. So you have u, sine u, and v. And you're going to have u go from negative 2 pi to 2 pi, say. I don't know what I say for the parameter. Do I tell you negative pi to pi or anything like that? Oh, negative pi to pi. Okay. And the v go from negative pi to pi as well. Am I off the chart there?
You have to charge Burns.
Yeah, I'm off the chart. I'm off the charts anyways. Yeah, that's true. Okay, that'll do it. That is y equals sine x. Okay, this is going to move parallel to the z-axis. And on the other one, you have x equals sine y. It's all the same, except that's x equals sine y.
Just was talking about something 2D.
Yeah. No, do that, just that. And you'll see what happens. It's kind of cool. You got ribbon candy one.
How would you define a plane in that? I've never done that.
You ready? Here we go. We have a couple of planes here. Here's a plane. Here's what you want to do. You define this to be f of x, y. You see, when you have z equal here, z equals 10 minus x minus y. Z equals this. Well, z is a function of x and y. What you want to do in Mathematica is define the function, and I think I have this in the lab, this f of x comma y, this construct there, I think. When I do a plot 3D, I'm pretty sure I have that.
sphere, but you gotta
Okay.
do it for a plane.
Okay. For the plane, it would be this. That's your z. So that z is equal to 10 minus x minus y. And then you would do a plot, 3D, like so. And have your x go from, I don't know, -4 to 4 or something. And your y go from, say, -4 to 4. And that would give it to you. That would do the plane. All right, what else we got? Yes, Omar.
The question about finding lines that were the same.
Lines are the same, yep.
Yeah. How did you plug in the t values back into the equation with the s?
Okay, hold on a second. Lines that were the same was,
The one up below?
this one here was the same?
No.
This one here?
Yes.
Okay, so what do you want to know?
So you said if t equals 0, you found the value.
Yes, got it.
So how did you plug those in?
What I did, I let t equal 0 and found the point on this line was 1, 2, 0. Okay. Then I went over here and said, what value of s will cause this x to be 1?
Oh, okay.
And s is 1/2. Now the x is 1. Now keep that s. Are the y's and z's also the same? And it turns out, yes, they were. So we had the same line. This is one benefit of doing having this document camera. You can refer back. Okay. What else you got? Any other questions at all? What? That's it? So tomorrow, we do the same thing again. Oh, man. All right.
I'll go grab a few
Whatever.
I have a quick question.
Bring them in. Go ahead.
What is on the web assign, chapter 11.7 is due next Monday, and is that going to be on the exam? Because it's a different due date than all the other web assigns.
What is it? 11.7? What is that? The cylindrical spherical coordinates?
You wrote that on the roadmap, so.
Yeah, it is on the roadmap. You have to convert. I give you a point in rectangular coordinates and ask for the R for cylindrical or the rho for I do that. But it's given in rectangular, and you have to give me R or theta or something like that. When's it due? That's due when?
That's due next Monday, and then the other ones are all due this Friday.
I don't know. That's a Burns glitch. I don't know. I don't know why that's different. I don't know. I have no idea why.
So it'll still be due next Monday, though, right?
Yeah. I'm not going to. Oh, because you mentioned it, you think I should change it back?
Well, I was just wondering. If
No, I wouldn't change it back. It's fine. Yes?
Do we have to do those exam web?
No.
Oh, okay.
No, those are for practice. Those are for laughs. What's that?
Alright. Yeah, I was just confused why they were there.
They're there because I figured, well, maybe you guys, you're sitting around some Saturday morning and, wondering what to do, and, there's something right there.
I know that feeling.
Yeah, see, there you go.
Drive in your inner heart.
See you guys.
Some recreational math.
Yeah.